Now let's move on to the next part.
So I explicitly went over that the functional purpose of chylomicrons and VLDLs is to deliver energy in the form of triglycerides, the adipocytes and myocytes, and phospholipids, not to deliver cholesterol to any darn cell in your body. So spend your time reading on it. That's what they do. You could even make the case that if they're not delivering cholesterol, why is cholesterol even in their particles? And it goes back to something what Peter said. These particles have to be spherical. So when a VLDL or an enterocyte is starting to lipidate ApoB 48, or especially the liver, ApoB 100, if you put cholesterol in that, and we have proteins that do that, microsomal triglyceride transfer and other cellular lipid transport proteins, by putting cholesterol on the ApoB, it becomes a spherical particle. So all primordial VLDs and chylomicrons are first just very cholesterol-rich spherical particles. They don't have the triglycerides yet. Then when they're spherical particle, they can really fill up with their triglycerides. So the cholesterol is in there for a structural property to make them spherical particles so that they can carry more triglycerides. And that's why when they go out, they become smaller spherical particles that are triglyceride depleted, and they just bring their cholesterol back to the liver or the intestine, and they do whatever they do with it. So that's why cholesterol's in there. They're not bringing cholesterol to my nose or your kidney or any place else because those cells need cholesterol. Those cells will make it, or they'll get it.
Okay, so let's just make sure we understood what he said. So he's saying that those lipoproteins aren't really there to deliver cholesterols. Well, if that's the case, he asks, why is cholesterol even in their particles? And it goes back to what Peter said. They have to be spherical. So by putting cholesterol on the ApoB, it becomes a spherical particle. So all primordial VLDLs and chylomicrons are first just very cholesterol-rich spherical particles. And mostly cholesterol to make them spherical. That's what I'm understanding here. The cholesterol is there for a structural property to make them spherical particles, right? So I think I got what he tried to say there. And, when I heard that part, I stopped a little bit and I thought, well, I'm, I'm not a lipid specialist and I don't have any research background. I'm not a structural biologist by any means. Um, I don't, I don't know. Wow, really? And sometimes I read papers or I come across something and I get really intimidated because it's not my field and it seems very complex. So here we're talking about structure of a new lipoprotein and how it forms, and that seems very involved. So I get a little bit intimidated when I read such complicated things or hear such complicated things. But some of you know I have a classics background, and so I remember Aristotle and his idea of going back to first principles, right, from the Greek word arche, to go back to the beginning. So, in the science of nature, as elsewhere, we should try first to determine questions about the first principles. And so, whenever I get intimidated or I don't understand something, it helps for me to just think through my first principles. And in this case, I found it really helpful because I suddenly remembered my cells. And my cells are these spherical structures formed entirely through physical processes such as intermolecular forces and thermodynamics, right? These amphipathic compounds disperse in aqueous solution to form these globular, these spherical structures that we call micelles, as you can see here. And you'll note there's no cholesterol there. There's no cholesterol needed there. So I think that this might actually hold a clue for all of us. And I think that here is where, first principles might triumph a little bit. So, I think we can hear the same celebration of first principles with Dayspring.
Rutgers. Medical school is inconsequential. I learned everything in Rutgers pre-med, at least the biochemistry and the physiology anyway.
So there you go. I mean, I think it's really important sometimes not to get too caught up in maybe the complexity of things. And we can go back to the basics, especially if you have a strong basic background. This can be very helpful to, thinking through some of these more complex problems. So looking at ApoB lipidation, we see here in this paper that the addition of phospholipids to this site may be important and sufficient for the assembly of secretion-competent B lipoproteins, phospholipids, right? Not cholesterol. Again, these proposed micellar structures, yay, first principles, would have an external surface of relatively randomly oriented hydrocarbon chains with certain regions stabilized by the head groups of phospholipids again, all right? And here, Journal of Biological Chemistry 2015, we demonstrated that the first 1,000 amino acid residues of human ApoB100 are required for the initiation of ApoB containing lipoprotein assembly, and that this primordial ApoB particle is phospholipid rich, okay? So yeah, it turns out that it's not cholesterol rich, and it's not cholesterol rich because we don't really need cholesterol to form spherical structures, that micelles are really naturally how these amphipathic and lipid products kind of aggregate in solution. And then I decided to investigate, curvature of membranes, because even though we know that micelles will make them spherical, I just wanted to look at curvature of membranes. And I thought Dr. Tia would be interested in this because he has a background in mechanical engineering. And my brother studied mechanical engineering when he was in college, and he's interested in these things. So maybe I'm projecting here, but I think he would be interested in looking at curvature of membranes. So I threw this in, and it says for cellular membranes, positive or negative curvature is determined by curve directionality toward or away relative to the compartment of volume contained by the membrane. So positive curvature builds a sphere, so it's kind of round like this, while negative curvature is in the opposite direction, like at the neck of a vesicle budding. That's interesting. And it turns out that cholesterol has intrinsic negative curvature. So it's actually kind of anti-spherical. So my clarifications here, primordial ApoB is not actually cholesterol rich. It appears to be phospholipid rich. The lipids aggregate in spherical structures through physical processes, so those micelles. Cholesterol does add rigidity to membranes, and cholesterol causes negative curvature to membranes. So actually it's anti-spherical and is involved in the formation of budding structures, okay? So I think important to remember.